So today in this video we're gonna talk about the dipole moment. So in atomic molecule, more electron negative bonded atom attract a shared pair of electron move towards itself. So that results in partial separation of charged unbonded atoms named as a polar molecule. So extent of polarity of polar molecule is determined by the dipole moment. So let's say we have a diatomic molecule and one is obviously will be more electronegative and another will be relatively the more electropositive, and let's say the distance between them is d, and the charge on one is plus q and the charge on another is minus q. So that is defined. So extent of polarity of polar molecule is determined by dipole moment. So actually it is written like dipole moment is mu, that is equals to q multiplied by the d, and q is the charge on each of every atom. It could be a partial charge or it could be a full charge, because when the partial shifting of electron is there, the charge will be not exactly the plus 1 charge. In that case we're gonna write it as a q multiplied by the d, or so here what will be in the unit will be like a coulomb meter, or it could be also written as dBi. So let's say we have a molecule here. A is having a B. A is forming a bond with B. So here in that case we gonna like a separation. The charge will be like here delta negative and here will be delta positive. So that's how the charge is being separated when we have a covalent bond, and like electronegativity of A is greater than the electronegativity of B. So that's how there is a separation of charge. So it is defined as product of magnitude of either positive or negative charge, and they must be same. However, in the positive charge that will be same as negative charge because of the conservation of charge. Total charge summation should be 0, and distance of separation between these two charges. So it is defined as the product of magnitude of charge and the distance of separation between these two charges. It is a vector quantity represented by arrow sign. It is represented by arrow sign. The direction is towards negative end. From positive end it is directed towards the negative end. Its SI unit is coulomb meter and CGS unit is ESU centimeter, or common unit is dBi. So if we're gonna talk about what is the charge on the electron, so charge on the electron is given by like 1.67 into 10 to the power minus 19 coulomb, and in that case, and it is also written as 4.01 into 10 raised to the power minus 10 electrostatic unit ESU, and we know 1 ESU that is equals to 1 by 3 into 10 to the power minus 9 coulomb. So that is the relation between ESU and coulomb, and 1 dBi that comes out to me. dBi is the unit of dipole moment, that is 1 into 10 raised to the power minus 18 ESU centimeter. And if we put the value of ESU in coulomb, so it is 1 into 10 raised to the power minus 18 multiplied by 1 by 3 into 10 to the power minus 9 into, if we convert that centimeter into meter, into 10 raised to the power minus 2, it is coulomb meter. So it is 10 raised to the power minus 2 coulomb meter. So 1 dBi hence comes out to be, after solving this we're gonna get it like 1 by 3 into 10 raised to the power minus 29 coulomb meter. So that is the 1 dBi if we want to get in coulomb meter. If we want to calculate in CGS unit, it will be 10 to the power minus 18 ESU centimeter. Now there are some important points regarding the dipole moment. So we're gonna deal like whenever we have a symmetric molecular species which is symmetric in shape and structure, in which bond pair and lone pair is also symmetric, placed has a zero dipole moment. So let's see a case like if we talk about a CCl4. So we know what is the structure of CCl4. It is a tetrahedron. A chlorine is attached. 4 chlorines are attached with the central electron carbon, and all the bond angle are 109 degree, and it is 28 minutes. So here that is the angle, and 4 chlorine are attached with carbon. So it is so net dipole moment will be 0 because it is symmetric. We're gonna talk about like AlCl3. Al, here chlorine we have, here chlorine we have, here chlorine we have. So actually what is the direction of the dipole here from positive end to negative end, because chlorine is more electronegative, so it will be having like delta negative, it will be having delta positive, so it is directed from positive to negative. Here also it is directed like this, it is directed like this, it is directed like this. In AlCl3 it is also being directed like this from negative to positive. In that case mu will be 0. If we're going to talk about like CO2 molecule, in that CO2 molecule, it is gonna be from negative to positive, from positive to negative. Here it will be delta positive and delta negative, delta negative. So here that will be the bond, the direction of the vector. And actually what it represent, this sign represent the electrons shift towards. So this vector means the electron is shifting from positive to towards negative. So it is showing the movement of electron also. Like if we're gonna talk about XeF4. So in XeF4 it is also like XeF F. It is a planar molecule and it has 2 lone pair over there. It is also symmetric, and the direction of electrons are from positive to negative. More electronegative means towards the more electronegative. So these all 4 are known as a non-polar also. So they have don't any polarity. The net shifting of electron, the direction of electron is 0. That's why it is also known as a non-polar. Now let's see one more important point. In case of diatomic molecule, its bond dipole is a dipole moment of whole molecule. But in case of polyatomic molecule, dipole moment of whole molecule is calculated by vector summation of all bonds, dipole and lone pair of dipole, as follows. So actually we have seen how the vector is shifted. Like let's understand it through an example. We have here H2O, water molecule, and we have like its original structure. It has 1 lone pair this side and 1 lone pair this side. As we know, these it is like tetrahedral structure. So we're gonna direct every bond pair and lone pair. So here we know electron gonna shift towards this side. Here electron also gonna shift towards this side, and here also electron gonna shift towards this side, and here also electron gonna shift towards this side. Now let's say the angle between them is theta. So let's say here the dipole moment is mu1, here dipole moment is mu2, mu1 also same, because we know that how we calculate mu, it is the charge. What is the charge distributed between these particular bond, and what is the distance? So mu equals to q multiplied by d, and it will be same in the both case. So let's say the resultant is written by r. So r is given by like root over mu1 square plus mu2 square, mu1 square plus mu1 square plus 2 mu1 mu2 times cos theta. So that is the resultant vector towards of that particular in that direction, that is known as r. So let's say here also it is like mu2 and it is also mu2, and the direction that is towards this, and let's say it is r1. So what will be the net dipole moment? So net dipole moment will be of whole molecule that will be like r plus r dash. So that is the net dipole moment. So we know that whenever we have a vector here, like here let's say it is mu1 vector and it is mu2 vector, and the angle mu1 and let's say these are same. If they are different also we use this formula and angle theta. So net resultant vector is given by this formulation, r equals to formula mu1 square plus mu2 square plus 2 mu1 mu2 mu1. In here also we will be using mu1 because both are same, cos theta, and when they are different the resultant vector is given by mu1 square plus mu2 square plus 2 mu1 mu2 cos theta. So that's how we have this formula, or now it is also mu1 square plus mu1 square and 2 mu1 square cos theta. So it is 2 mu1 square plus 2 mu1 square cos theta. So that's how we could solve whatever is the theta, and we know that net resultant vector here is this side, and is in that case both are the net resultant vector is this side. So if we add both of this vector, we're gonna get the net result over here. So here now if we're gonna look at one example, like we have H hydrogen fluoride and we have HCl. Now let's compare the dipole moment of these two. So as we know that the charge increases, and here charge is more and distance is less. We know fluorine is a very most electronegative element in the periodic table, so the charge separation will be highest, but the distance, because it belongs to the second period, so the distance is not that far from hydrogen. And here if we compare the HCl, so here now if we say like charge here is relatively less but distance is more. Now if we compare their dipole moment, it's mu and it's also the dipole moment mu. So here we know mu comes out to be like charge multiplied by the distance. So here this value, the HF is more, the dipole moment. So when we are comparing the dipole moment among polar molecule, charge is the dominating factor over the distance factor. The charge factor is always dominate than the distance factor, but there is an exception. So in that exception, like we have a Cl and we have CF, this type of bonding we have. So if we want to calculate its mu, so in that case here the distance factor that dominates over the charge factor. What does it mean? So here we know there is some charge separation and there will be delta positive, delta negative here. Similarly here there is charge separation and we write as a delta positive and delta negative here. So we know that the value of charge is more but distance is less. Here value of charge is relatively less but distance is much high, that if we multiply both of them we are getting this value more. This value of Q multiplied by D is more, which is mu. So mu of CCl is greater than CF. So like if we write the order of dipole moment, so order of dipole moment like will be, if we see will be like CH3 or Cl is greater than a CH3F is greater than CH3 of Br, will be greater than CH3I. So here we know in both of these cases the distance factor dominates over the charge factor. But in that case, the charge factor dominates over the distance factor. Now let's see what is that is in HF. Now if we look like HF, HCl, HBr and HI. So in that case, like HF is greater than HCl, HBr, HI. It is regular. Here it is following the regular thing, where in the regular thing charge factor dominates over the distance factor. But we have to again, this is the regular thing, but we have to again see this exception in case of CCl and CF. Now let's talk about the aromatic compound. So in case of aromatic compound, when both substituents are either withdrawing or either releasing group, then dipole moment of ortho isomer is highest. So now let's see when we have a three type of isomer. One is ortho isomer, one is like meta isomer, one is like para isomer. In that case, the ortho isomer dipole moment is higher than meta isomer dipole moment than para isomer dipole moment. So in that is high. So why it is high? When it is high, when both substituents are either withdrawing group or either they are releasing group. But when one of the substituent is electron withdrawing and another is electron releasing, then dipole moment of para is highest. So let's talk about the, here we have NH2 and here we have like NO2. Here we have like NH2 and here we have like NO2. Here we have like NH2 and here we have NO2. We know that NH2 is having a para effect. Means the where is the direction of bond here? So actually it is releasing group. NH2 is releasing group and NO2 is the taking group. Here it is also releasing group. Here also it is taking group. Here also it is releasing group and here is also a taking group. So in that case, the para isomer, the dipole moment is highest. Then if we compare the ortho and meta, so maximum is of para than meta than ortho. Now let's talk about like in that case, like when we have here chlorine and here also we have like chlorine. Here we have a chlorine and here we have also chlorine. Here we have chlorine and here also we have chlorine. So in that case, like we know the direction of movement of electron will be towards the chlorine. Here also because minus I factor dominates over here. Here also in this side and here this side and here this side. So in that case, meta isomer will be more than para and also will be the highest. So it is generally vector sum. So in that case, if we see like here mu of meta isomer, that is exactly equal to the mu of chloro benzene. Why? Because the net direction is towards this side and that mu is exactly equals to chlorobenzene. If you put the value of cos 120 degree, you will get like it is coming equals to mu. So here also meta para, in that case this will be the direction. Like if you see the cyanide compound Cn, so in that case Cn, if we have so here this is the highest than this than compared to this. This is the journal what we follow while saying that we know it is a electron taking group. So when it is electron taking group, both are electron taking, electron withdrawing, then we have seen that case, and one is electron taking and electron withdrawing, we have seen that the para is the highest. Now if we gonna see, let's consider here we have NH2, here also we have NH2, here we have this case, and here we have also NH2. Now here also, like if we're talking about para side, or here we have like OH and OH over here. Here we have like OH and OH over here, and here we have like OH and OH over here. So we know both have like both are same here, both are the electron withdrawing, here also the electron donating, here also electron donating, and here also both are electron taking. Okay, electron donating, and here also electron donating, and here also it is the donating one, and it is also donating one. Now we know, when we have seen when both are same, then ortho is greater than para. It is ortho, it is meta, and it is para. Here also it is ortho, here it is meta, and it is para. So these are greater. Is NH2 is 0 or is 0? Yeah, this is important, that they are not mu here not equals to 0, and mu here also is not equals to 0. So why it is not 0? The direction of both are same. So here the sum torque is developed. So what does torque here is meaning? So like if we have this NH2 structure, so in that case nitrogen will be here and the 2 hydrogen will be here. But in that case, like 1 nitrogen is here and the direction of 2 hydrogen is here. So if that is okay, then this one vector is getting cancelled. But there is one more vector. In that case, that we know that the electron is going towards the nitrogen. Here this is the direction, and here this is the direction. So here it is this direction, here it is this direction. A little bit different is there. So here there is some torque is between developed. So here like there is some direction, and if you see the direction of H and H over here, so they are a little bit different from this direction. Let's understand by this OH and OH method. OH and OH. So what is there actually? If we have like two different OH structure, here O and H, and here O and H, like one will be their molecule, and we have one more OH, like one OH is like this, one OH is like this. So we have seen there is a bond here also, but what is happening, there is also dipole moment by this bond. So here the dipole moment is towards this side, and here dipole moment is towards this side. So is in that case the net dipole moment of until this compound is 0. But if we go towards this, one vector here and one vector here, so its resulting is like this. So in that case mu is not equals to 0. But if we see this case, here one direction is this, one direction is this. So in that case mu will be equals to 0. So if we talk this journal compound, in that journal compound we will be getting like mu is not 0. Here it is not equals to 0 because it may have both these cases. Similarly in case of NH2, like we have N1H and 1H this side, and N1H and 1H this side. Another case like N1H and 1H this side, and N1H 1H this side. So in that case, one of the cases will be there when dipole moment is not 0, and this is called the torque. This torque is developed, so dipole moment is not equals to 0. So here also dipole moment is not equals to 0. Now let's see calculation of percentage any connected and covalent bond is also done by the dipole moment. So like we have what is the percentage of ionic character in a covalent bond? That is given by formula mu experimental divided by mu theoretical. So mu experimental is experimental dipole moment. How we calculate the dipole moment experimentally, and mu theoretical is theoretically what will be the dipole moment. Like if we take the example of HCl, so here we have H and a Cl, where H having a delta positive charge, Cl is having a delta negative charge. So what is the mu theoretical? Mu theoretical is coming out to be like Q multiplied by D, and theoretically we consider this 100% ionic bond. Theoretically we consider it is a 100% ionic bond. So we take charge when we remove the bond, and H will be getting +1 charge and Cl will be getting -1 charge. And mu theoretically will be coming out to be like 4.8 into 10 to the power minus 10, which is ESU, into 10 to the power minus 8, which is distance. Okay, so that is distance is like D. Let's say distance is D, but that is the ESU centimeter. So here 4.8 into 10 to the power 8, that is the distance, and it will be like 4.8 into D, that is dY. So we know 1 dY equals to 1 into 10 to the power minus 18 ESU centimeter. So that is actually this and ESU centimeter is giving dY. So that's how we do calculate the theoretical dipole moment. So theoretical dipole moment, we know it is Q multiplied by D, and charge we know that what is the charge, and here we will multiply the distance. So we will be given like this experimental will be given, and theoretically we need to calculate. So when we calculate, we should be knowing now all these ESU value and the charge of, this is the value of charge in ESU of a single electron, and that is the distance. So it is ESU centimeter. Convert that ESU centimeter into dBi. So that is a dBi. So here that's how we do calculate the percentage of ionic character through this dipole moment.